Hey, y'all, welcome back. Let's take a look at this review and see if we can't solve all these problems. So this test is going to be going over the law of sines, the law of cosines, and the couple of area formulas that we went over on the last day. So let's start. It looks like for the most part we are just solving triangles, and we don't really get to area until a little bit later. So just take this one at a time and see if we can't solve these. Now for each one of these, I would highly recommend drawing a picture. I think, picture says 1,000 words, and I think it will help you sort of visualize whether you need to use the law of sines, the law of cosines, if you have a diagram to help you out. So a lot of these will say law of sines on the test. I'm not going to tell you whether to use law of sines or law of cosines. That'll be up to you to figure out. This is just going to be kind of a little hint as we're going through the review. So here, looks like we do have an obtuse angle here. So I just want to, try to draw one. This is not going to be drawn to scale, but I'm going to make it, reasonable here so that I know that this is 125 degrees. Call that angle C. And I'll pick one of the other angles to be B, so it doesn't really matter which one. I'll just pick this one. And then we know that C is 10. Now, this review is kind of set up similar to the test, where you're not going to have to find or solve for the entire triangle on most questions. Most questions are just going to ask you to solve for one of the components. So you're not going to have to go through the entire solving process on every single question. There might be a few where I ask you to get all of them. But for the most part, you're really only going to be required to find one of the components. So like in this question, it's only asking you to solve for B, okay? So side B is going to be this one right here, right? So you don't need to get angle A, side A, or any of that. So this is just going to be a direct application of the law of sines here. So we'll use C over sine of C, because that is the pair that we have, equals B over sine B. Okay, so I'll just go ahead and plug in what I know about that, which is everything except for my unknown, which is sine B. So sine, or 10 over the sine of 125 equals B over the sine of 31 degrees. So now this turns into a calculator problem. So so B, when we solve for that, is going to be 10 times the sine of 31 degrees, all divided by sine of 125. Okay. So B is going to be approximately whatever we get when we type that in the calculator. So let's do that. All right, where is my calculator here? Isn't it showing up? There we go. Okay, back in business here. Okay, so we've got, let's make sure we're in degrees. Okay, radians is going to be the default, so we want to check on that. And so we're going to go ahead and type this in. Ten times the sine of 31 degrees over sine of 125. So we get approximately 6.287. Okay, so there's number one. All right, so number two, looks like a very similar setup. Oh, it is actually the same triangle, except now we're trying to solve for A. So this is just going to take us one step further here. So at this point, we have the exact same triangle, but we know what B is now. Now to find side A, we don't actually need to know side B. So it's really not going to be even relevant here. But to find side A, what we need first is we need to find angle A. So to find angle A, we're going to subtract both of the other two angles from 180. So 180 minus 31 minus 125. Let's see what that is. 180 minus 31 minus 125. You get 24 degrees. So angle A is going to be 24 degrees. And we'll use that in our law of sines with a very similar setup as what we did before, except that instead of B, we're going to be working with A here. So we'll have A over the sine of 24 degrees, which is what we just found. So A should be equal to 10 times the sine of 24 divided by the sine of 25. And we need to type that in. And we get about 4.965. And there's side A. Okay, no big deal. So for number 3, we're given two angles and another side. We're going to have to use law of sines, but notice that we don't have a pair here, which is not necessarily a problem, because we can subtract the two angles we know from 180. So let's see, so this one is going to be, call this angle A. Well, 14 degrees, looks like the small one's over here, so I'll just put A over here. It doesn't really matter where these go. Okay, call angle C 82 degrees. And then B is going to be, see, so this is angle B up here, and side B is over here. All right, so really what we need is angle B here, so we can have this pair and use the law of sines to find the other two sides. So let's find that missing side here, a missing angle rather. So angle B will be 180 minus 82 minus 14. And so angle B will be 180 minus 82 minus 14. It's 84 degrees. Okay, so now we've got this angle up here, and if we're trying to find C, right, we're trying to find C, it's going to be opposite of angle C. So we'll use this pair of B's for our law of sines here, and we'll use that to solve for C. So here's our pair for B, 40 sine of 84, and then I'm trying to solve for side C from the sine of 82. So this will end up being 40 times the sine of 82 divided by the sine of 84. Go to the calculator, make sure this is C. And so let's see what we got here. $40 times the sine of 82, 82 divided by the sine of 84. Okay, so we get about 39.82, and that'll round up to 9. All right, so with number 10, we're given all three sides, so we're going to use the law of cosines. Now, let me show you which version of the formula I'm going to give you here. Go ahead and type it in. So yeah, c squared equals a squared plus b squared minus 2ab times the cosine of angle c. So this is just like a generic formula that you can use. They don't need to necessarily be these particular sides and angles, but you do need to make sure that whatever side you want to isolate here, that this right here, let's see if I can, well, you know what, I'll just underline it. But this side right here needs to correspond to this angle. Okay, these other two sides, you can change, you know, it doesn't matter which one's which, but just make sure that whichever angle you're looking for is going to match up with this one. So for instance, in this case, we've got a triangle that's XYZ, and we're going to use the law of cosines to solve for the value of capital Y, which is going to be the angle Y. So in other words, since we're trying to solve for angle Y here, we're going to put angle Y here and side Y here, and these two will be the other two sides. So in this case, like X and Z. So we do want to modify this to match the triangle that we have. And let's sketch this triangle. It doesn't have to be to scale or anything, but just to get an idea of what it should look like. So this, we'll call this 6, X equals 6, Y equals 11, and Z equals 8. Again, it doesn't really matter which one you select, like where you put X, where you put Y, where you put Z. But what's important is that the angle measures are opposite of the correct angle. So in other words, like if side Z is here, angle Z has got to be up here. If X, side X is over here, angle X should be over here. So just make sure that your angles correspond to your sides here. So we're interested in finding angle Y, which is going to be this one, right? So, so we're going to rearrange this equation, or rewrite it using the appropriate variables here. So we'll say y squared So y squared equals x squared plus z squared minus 2 times x times z times the cosine of angle y. So just to point out a couple things again, I want to emphasize that the x and z are interchangeable here. You can reverse these. Both addition and multiplication are commutative, so the order here doesn't matter. Just make sure that these two sides are not the ones opposite of the angle you're searching for. So now we need to solve for angle y. So that's going to require us to subtract both of these two terms over to the left-hand side and then divide by this negative 2xz. So if we do that, if we do both of those steps, we're going to get cosine of y equals y squared minus x squared minus z squared, all divided by negative 2xz. And then if we want to isolate angle y here, we'll get the inverse cosine of y squared, really just that whole thing. I mean, might as well just copy and paste it. But at this point, we are going to just substitute in all of the values that we know and put this in our calculator. We should get our angle. Just gonna clean this up a little bit here so we can fit the last step. Okay, so angle y will be equal to the inverse cosine of, now I'm going to just, again, copy and paste this because I just want to fill in the values here. So I know all these side lengths, y is 11, x is 6, and finally z is 8. too many parentheses there. Okay. And then, so yeah, now we're going to go ahead and plug that into the calculator and make sure that we are in degrees, and we should be good to go here. So we get the inverse, not cosine, we want the inverse cosine. Let's make sure, yep, calculator tends to reset itself here, this little emulator we got going. Okay, so we get the inverse cosine of big fraction here. So I've got 11 squared. I'm just going to type it in exactly how it looks. I'm not going to try any funny business, trying to, don't want to get cute with this. Just type it in exactly how it looks. And then we should be safe. All right, so we get okay, so that's interesting. So we do get an obtuse angle here. Okay. Yeah, so we get 102 about 130 degrees. All right, so that would be our solution here. We don't have to solve the rest of the triangle because it only asks us to find angle y. And that's going to be kind of similar to how the questions are going to be worded on the test, where you're not going to need to find necessarily every single side every time, or angle. It'll typically just ask you for one. Okay, so you don't have to go through the entire process for every single problem. That would take a while. We're still using law of cosines, but we want to find angle x. So we're still going to use this formula up here. Oh, I can't see what I'm pointing at. There we go. Okay, we're still going to use this formula up here, but what we need to do is solve for this angle measure. Okay, so the first thing I'll do is just copy this equation and then replace everything with what I need. So I know angle x. I'm going to replace that with this, and I'm trying to find side. Oh, you know what? I'm trying to find side x. This is going to be even easier. I don't even need to solve for this. The other two sides here are going to be y and z. Okay, so just to get an idea of what this triangle is looking like, let's try that one again. There we go. We know x is 50 degrees, so we'll just call this one 50. And we know y is 3, so we'll call this side y, and this side z. Looks like we got a side angle side scenario brewing here. Alright, so we're trying to solve for this side x. We're going to need to take the square root of both sides, and I'll just kind of do that and substitute everything right after that. So just take the square root of this entire side here. Oops. You know what I'm going to do? There. There we go. Okay, so now let's plug all the values in that we have. Okay, and then we've got 50 degrees goes here. All right, so now we're just going to type that into the calculator. 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine of 50 degrees. I think I'm still in degrees here. Let me just double check. Yep. All right, so there we go. There's side x. Should be about 3.094. And here we're getting into area, so we'll just have to make sure to use the correct formula here. So it looks like we're going to have a side angle side here, kind of like the previous one. So in fact, any chance I get to copy and paste here, I'm going to go for it. All right, so here we're going to say that, you know what? I'm not going to copy and paste that. Forget it. Because this is going to be an obtuse angle, so my triangle's really not going to look like this. This thing is like really lagging here. What is going on here? All right, so 106, if 90 looks like this, 106 is going to be a little bit more open than that. So I'm just going to estimate. That angle is going to be 106 degrees. Let's say P is 15. And C is 21. Okay, so we are going to use a formula that's going to be given to you, 1/2 times each of the sides that are given, so 21 times 15 times the sine of that given angle measure, 106. And this is going to be something we plug into the calculator, just like all these problems. So we got 1/2 times 21. Oh, oops. Let's get out of that fraction. There we go. All right, so times 21 times 15 times the sine of 106. And it looks like we get 151.398. Really, let's be clear here, this is the area. So the area is going to be approximately 151.398. It's going to round up to 399. Finding area again, but we got a side scenario. Okay, should not be equilateral. Side lengths are approximately, they're pretty close, but the longest one here should be y, 7.1, and then finally z is 5.9. So we're looking for the area. This is going to be one where we use Heron's formula. Again, that'll be given to you. So just to be clear, Heron's formula is the square root of the semi-perimeter times the difference between the semi-perimeter and then each side length. So what's important here is that we calculate the semi-perimeter first, and that's what this S stands for, okay? So the semi-perimeter, which is S, is half the perimeter, okay? So that's going to be 4.3 plus 7.1 plus 5.9, all divided by 2. Don't know that off the top of my head, so we'll have to calculate that. So get 8.65. So that's going to be what I get for S here. So I'm just going to go ahead and substitute everything in here. So S is 8.65. Now we don't have A, B, and C. It doesn't really matter which one's which here. So in fact, I should probably go back and just call this X, Y, Z instead. It doesn't matter which one's which. Just make sure that each one is represented once. So we're going to have 8.65 minus 4.3 8.65 minus 7.1, and then 8.65 minus 5.9, and I'm going to type this into the calculator. Here we go, 8.65. There's 8.65 minus 4.3 times 8.65 minus 7.1 times 8.65 minus 5.9. All right, so my area is going to be approximately, thank you, 12.664. There we go. All right. Number 8 says find the area of a parallelogram with side lengths 40 and 48 and diagonal lengths 16 and approximately, we'll just call it 87. So here we have a parallelogram. I'm going to go ahead and sketch that out. And then we'll label all the sides. This is not going to be drawn to scale, so don't bring your ruler up to the screen. But yeah, so here's an approximation of the parallelogram. It says the sides are 40 and 48, so I'll label this longer side as 48. And I'll label the shorter side as 40. It says the diagonal lengths are 16 and, like I said, a little under 87. So I'm going to draw these diagonals on here. Oh, that does not look good. Let's try that again. Okay, so we got this diagonal. And I guess I'll do this other diagonal in blue. Okay, the shorter one's 16. And we're trying to find the area here. And what you'll notice is, as we draw these diagonals, what we're seeing is that this parallelogram is being split up into 4 separate triangles. And so our strategy here is going to be to find the area of really just 2 of these triangles and then double it. So, or in other words, just find out the area of all 4 and add them together. But you don't really need to find all 4 separately because these 2 triangles on the side are congruent, and so are these 2 triangles here and here. In geometry, you might have used like a side angle side similarity or congruence theorem to show that, but you don't need to worry about that. Just as long as you know these 2 triangles have the same area and these 2 triangles have the same area, then what we're going to do is find the area of this one, the area of this one, add those together, and then double it to get the total area. So that's going to be kind of our overall strategy. So let me finish labeling this for you. This shorter diagonal is 16. And so that means each half of this, because these diagonals do bisect each other, is going to be not 4, but 8 and 8. So, oh, my line disappeared there. Not sure what happened. Let's put that back in there. Okay, so yeah, so this would be 8. That 8 is not the full diagonal. Remember, the full diagonal 16. This is going to just be labeled 8 and 8. And really, that's just for convenience sake. I'm not even going to label this over here. I'm just going to label this 8 as being from here to here, because this is the side I'm going to use to find this triangle. So the other one is 86.902, and I guess what I need to do there is divide that in half to get the length of half of this diagonal. And I'm typing it in my calculator right now. Divided by 2, 43.451. Okay. So we'll go ahead and label that. Maybe I'll label this one 43.451. And I will also actually label this other one over here too. I didn't do that for the 8 because we weren't really going to use that other diagonal. But here I am going to use this other part of the diagonal to find the area of this triangle over here on the left. So basically what I'm trying to do here is set this up so that I have information about all 3 sides of this triangle, and then I can use the Heron's formula to find the area of this. Okay, So we're going to use Heron's formula twice. Okay, we're going to use one for this top triangle, one for this bottom triangle over here. We're going to get an area for each one, and then we are going to find the total area. So let's just get started here. So the area of the triangle on the left, what the, okay, why do these pieces keep disappearing? Don't know what's going on. Very annoying. Yeah, I don't know why that's happening. Okay, so this area over here, this left triangle, is, and I'm just going to go ahead and write out Heron's formula here. You do get this on the test, so you don't have to memorize the formula. So yeah, the area is going to be equal to the square root of the product of the semi-perimeter and the difference between the semi-perimeter and each of the three sides. So 8, 43.451, and 40. Now we have not calculated the semi-perimeter here. We'll go ahead and do that. But the semi-perimeter is going to be half the perimeter. So over here, I'll just calculate the semi-perimeter separately. This S is going to be half of the perimeter. So 40 plus 8 plus 43.451, all divided by 2. And let's go ahead and put that in the calculator as well. Make sure you're using your calculator for these problems. You do not need to do this by hand. All right, so I'm getting roughly 45.7255, 45.7255. We could probably round it, but I'm just going to stick with, try to be as precise as I can here. So this is what I'm going to plug into S. Now I've got this just crazy looking equation here that I am going to put into the calculator. All right, it looks way more complicated. I think if you're just looking at this, blindly, without looking at anything else, this looks kind of crazy, but really we just want to go ahead and start typing things into the calculator. So let's go ahead and pull up the calculator, and I'll pull it up so you can see what I'm typing into. Yeah, I guess we're gonna have to move it so you can actually see the formula. If I can grab it. Gonna let me? There we go. Yeah, let's move it over here. Okay, so let's get rid of all this. So we got the square root of 45.72. You know what I'm gonna do? This is gonna be a lot of typing. I'm gonna show y'all a little trick how maybe we can shorten this up a little bit. So notice we've got this 45.7255. That's our semi-perimeter, and that's kind of tedious and annoying to have to type that over and over again. So I'm going to use a little shortcut here. I'm going to store this value in memory. And so if you don't know how to do that, let me show you. You press this little store button, or the stow button, and you pick which letter you want to store this in. So I think kind of the obvious selection here would be S. So I'm going to hit alpha, and then we see the S here right above the natural log button. And so basically what I'm doing here is I'm saving this value in S. It'll make typing this equation a lot easier, because now I'm going to do the square root, and instead of typing in 45.7255, I'm going to hit alpha, natural log again, to get that S. Okay, so that is this number. I'm storing it in this variable. So times S again, so I don't have to retype all that, minus 8, and then times the semi-perimeter minus 43.451 times the semi-perimeter. Still quite a bit of typing here, but at least we can save a little bit there. All right, so there we go. So that is going to be the area of that left-hand triangle. So yeah, we got, what is it, 149? About 149.88 square units. I don't think there are any units set. No centimeters or meters, anything like that. So that's the area of this triangle. Now what we need to do is actually do this again, but do it for that top triangle. Okay, the right triangle will have the same area as the left triangle. So ultimately, I'm going to double this, but I'll wait until the next step to do that. Oh, it's not going to let me copy all that. Just didn't really have to want to type all this again. There we go. Okay, so now we're going to find the area of the top triangle. Okay, same thing here. In fact, the formula is just about the same. The only difference here is we have 48 instead of 40. So I'm going to change this 40 to a 48 for this last side. And then that also means we need to recompute the semi-perimeter, because we do have a different triangle here. So instead of 40, I'm going to have 48. And so, yeah, I'm going to have to type that in. I'm just going to do that real quick. 48 plus 8 plus 43.451 divided by 2 is 49.7255. Okay, so yeah, a little bit bigger than this one. All right, so what do we have next here? Yeah, so that's our S, and now I'm going to go bring up the calculator again. Let me pull that up so you can see what I'm doing. This is going to be kind of in the way, isn't it? Here, I'll put it down here. That's good. Okay, and I'm going to essentially copy this exact same thing. The only thing that's different is this 48, right? Before it was 40. I'm going to change that to 48. Oh, you know what? I didn't save the new S value, so I need to go ahead and do that. 49.7255. That's my new S. Almost made a mistake there by not typing in the new S. All right, so now I have this formula up here. I'm going to change that 40 to 48. It's the only thing that's different here. So, okay, we get about 149.88. 149.88. Wait a minute, is that the same? That's the exact same area there. Is this going to always happen? Is it exactly the same? Hold up. It is, okay, so wow, it is really, really close there. That's amazing. Look at how close these areas are. Part of me wonders if they're actually supposed to be exactly the same, because I do believe this 43.451 is probably a rounded number. So if I had to guess here, if I'm just going to make a conjecture here, we would have to prove it, you know, outside of this. But I'm kind of wondering if we do a couple of these problems, if we're going to find with this parallelogram that all four of these triangles do in fact have the same area. That was a little unexpected. I did not expect that to happen, but maybe I should have. Okay, well anyway, yeah, so instead of having to find two separate and then doubling it, yeah, we could just find one and multiply by 4, basically. So yeah, so the left is going to be the same as the right, the top's going to be the same as the bottom. Turns out the areas are extremely close to each other. In fact, they're like close enough to really just say that they're the same for our purposes. And so now I'm going to do 149. I'm going to add these together and then double it. You're probably safe to just quadruple 149.88. It's probably going to give you the same answer as what I'm about to give you. So this are the two areas added together. Go ahead and double that because we have the bottom and the right-hand triangles. And so we get about 599.52. So maybe I should break that down. So the total area is going to be the left plus the right plus the top plus the bottom triangles. We already know what all these values are. Okay, they're all going to be 149.88. So I'm just going to say that instead of adding that 4 times, I'm just going to say times 4. Just to be a little bit more, what's the word I'm looking for? Efficient with what I'm writing here. 149.88 times 4. Just curious, is that, yeah, basically that gives us the same thing with 2 decimals of accuracy. So 599.52 is going to be our final answer. All right, so that's how you can use Heron's formula to find the area of a parallelogram if you know the lengths of the sides and the diagonals. All right, that leaves us with one last problem, which is going to be kind of similar, except instead of using Heron's formula, we're going to use that other area formula that we have. So let's label some of this. It says, suppose that theta is 106 degrees. I'll go ahead and label that. Okay, so if this angle is 106 degrees, I'll put it down here. These 2 vertical angles are the same, so just to make this a little bit more legible, I'll put this down here because it should be the same as theta. And then so what we can do is, since we have a linear pair here, like these 2 angles lie along this line, so we know that they got to add up to 180. And 180 minus 106 is going to be 74. So this is 74 degrees. All right, and that also is going to be this one over here. If it helps, I'll label that too. But yeah. Okay, now it also says the lengths of the diagonal are 6 and 12. So we'll say the longer one is 12, meaning this side length right here is 6. Oops. This side length is 6. It's half of 12. And then the shorter side is going to be 3, because the short diagonal is 6. Okay, so now we've got this side angle side, and we want to find the area of the shaded region. Okay, so really these 2 triangles, like we said up here, are going to have the same area. So we just need to find the area of one of these triangles and then double it. So yeah, let's pull up the formula that we've used already a few times here. I'll go ahead and type it. There we go. Okay, so the area is 1/2 times the product of the 2 sides that are adjacent to the angle. So 6, so times 6, times 3, times the sine of 106. And this is something, again, we'll just put in the calculator. Throw a little degree symbol on there, make this look nice and pretty. Yeah, okay, well, there we go. Yeah, we just need to type this in. So let's get the calculator back out. 1/2 times 6 times 3 times the sine of 106. And before I hit enter here, I need to make sure, because the calculator defaults to radians, I'm going to go to mode and make sure that I'm in degrees. Otherwise, I'm going to get the wrong answer here. All right, and so we get 8.65. So we'll say the area of one triangle is, what did I say it was? 8.65. And so if we want the total area of the shaded region, we need to double it. Both of these triangles have the same area. So the total area would be 8.65 plus 8.65. So let's go ahead and double that. We'll just say times 2. And then so we get about 17.30. And that will be the area of the shaded region. So there you go. So this is the last problem on the review. Oh, okay, just kind of skipped around a little bit. This is the last problem on the review. Please reach out if you have any questions. You know, as always, I'll be here in the mornings for tutoring. If you're having any trouble with the law of sines, the law of cosines, any of these area formulas, I'm happy to help you out. But other than that, y'all, thanks for watching, and I'll see you next time. Have a great day.